Chapter 5, Quantum Theory and the Electronic Structure of Atoms. This chapter is probably one of my favorites because we can really delve into an atom and really understand the properties of an atom. What makes something flammable, what makes something stable, and it's really based off of the electrons. In order to understand the electrons, we have to look at quantum theory. So you can tell your friends, oh, I know quantum chemistry. This is just going to be a very general overview of quantum, however. But for example, we'll be able to look at this rainbow in this picture and understand why are there different colors that we see with this. On the bottom picture, we see different compounds that are being put on fire. So for example, in this one, let's say this is compound A. When you burn compound A, it gives off an orange color. Why? If I look at compound, let's say B, it gives off a red color. Why? And compound C gives off a green color. Again, why? We'll be answering those questions. Classical view of the universe. Since the time of the ancient Greeks, the stuff of the physical universe has been classified as either matter or energy. In Chapter 1, we talked about what matter was. We defined matter as the stuff of the universe that has mass and volume. So remember, it has to have those two things, mass and volume. Therefore, energy is the stuff of the universe that doesn't have mass and volume. We know from our examination of matter that it is ultimately composed of particles. When we look at particles, a lot of times what we're looking at are atoms, right? And it's the properties of those particles that determine the properties we observe. So if we understand the properties of atoms, because the smallest unit of matter are atoms, then we can understand how they react. Energy, therefore, should not be composed of particles. In fact, the thing that all energy has in common is that it travels in waves. So remember how you might have remembered at the beginning of class, I said we don't really look at anything other than matter in chemistry. I kind of lied, and I said, well, in this chapter, we're going to be looking at energy. And technically, energy is not matter. But we need to understand what energy is so that we can apply it to matter. The nature of light, its wave nature. Light is one of the forms of energy, and light is a form of electromagnetic radiation. Electromagnetic radiation is made up of waves. Okay, so waves, they look something like this. Electromagnetic radiation moves through space like waves across the surface of a pond. Let's talk more about waves. Every wave has 4 characteristics that determine its properties. You have the wave speed, wavelength, and we denote wavelength with this Greek symbol, which is known as a lambda. Okay, so lambda, you have to get good at writing it. And then we have frequency. Frequency, we denote it with this Greek letter called nu, and to write it out, it looks like a fancy V. And then also part of a wave, we have the amplitude. We're going to talk about these 4 properties next. So the first property we're going to look at is wave speed. So wave speed, all electromagnetic waves move through space at the same constant speed. That same constant speed is the speed of light. So no matter what wave you are looking at, all waves will travel at the speed of light. I should say all electromagnetic waves. So the speed of light is 3 times 10 to the 8th meters per second. Now let's talk about wavelength. This was the second characteristic of a wave. The wavelength is the length of a wave from one maximum to the next. Okay, so here is our wave. Let's write out what the different parts of a wave are. At the bottom of a wave, what do we call this point? We call this the trough. So that's the bottom of the wave. At the top, do you know what we call that? We call that the crest. Okay. So wavelength is the length of a wave from one maximum to the next. So here from one maximum, so from one crest to the next crest. So this is known as the wavelength. So it has to do one complete cycle, one full crest and one full trough. Different wavelengths will give different electromagnetic waves as well as colors. So for example, here we have different colors with a red wavelength. This is the first one. We notice that the wavelength is fairly long. So a longer wavelength will give you a red color. Then we have like a medium wavelength in comparison to the other three. This medium wavelength will give a yellow color. And then the bottom one, which is going to be very short, this is kind of a bluish color. So the blue I should say a short wavelength. A short wavelength will give a blue color when we're comparing them. Now, if we look at a rainbow, what wave or what color do we see at the very top of a wave or of the rainbow? We see the red on top. And then we see like an orange, yellow, green, blue, and purple. Purple is at the very bottom there. Okay, now if we are looking at these, we said that the red color has a very long wavelength. The purple color would therefore have a very short wavelength. And the reason why we have this separation is based off of how well that wave can curve. So a red wavelength, it's a very long, so it takes a very long time for it to curve down. That's why it's going to be on the very top. Notice how the red is just very, not very curved. Now, if I look at the bottom of a rainbow, which would be purple, the purple, that wavelength is going to be very, very short. So that could, because it's very short, it can easily bend. So that's why it's going to be on bottom. The third part of a wave is known as frequency. Frequency is the number of waves that pass a point in a given period of time. The units are going to be hertz, and hertz is Hz. Now we can also denote it as cycles per second, which would be denoted as inverse seconds, so s to the -1 power. Either one of these will be fine. So if you write hertz, or if you choose to write inverse seconds, either one of those would be fine. Label which waves have the lowest, medium, and highest frequency. Okay, so remember, frequency is the number of waves that pass a point in a given period of time. Let's say that this wave here, or I should say this time, is equal to 1 second. So as the wave goes from left to right, this is the time it takes to go 1 second. I want you to label which one would have the highest frequency, lowest, medium, that kind of thing. So go ahead and try that. The last characteristic of a wave that we will talk about is amplitude. Amplitude is a wave's height measured from the midpoint between crest and trough. And different amplitudes will give different brightness. For example, we have a wave on the top and wave on the bottom. Okay, let's look more specifically up at these waves. Okay, so if I look, are these wavelengths the same or are they different? Well, in the dim wave, I have a wavelength from here to here. And I have another wavelength from here to here. So basically I have two wavelengths shown. For the bright wavelength, I also have two wavelengths. So these wavelengths are going to be equal to each other. However, their amplitudes are going to be different. Notice the height. The amplitude, it says, is a wave's height measured from the midpoint between crest and trough. Okay, so you're going to be measuring it right here in the middle between the crest and the trough, like halfway through. So this is known as the amplitude. So even though both of these wavelengths have the same wavelength, they will have different amplitudes. The lower the amplitude, the dimmer the light is. The brighter the amplitude, or the higher the amplitude, the brighter it is. Wave characteristics relationships. We said that the speed of light, which is known as c, is constant, which is going to be 3 times 10 to the 8th meters per second. Now you don't need to memorize this number, but we will use it quite a bit, so you probably will end up memorizing it. But how did they even get this number? They found that if the wavelength and frequency were multiplied for any electromagnetic wave, a constant number was always produced. Isn't that interesting? So when they took the wavelength times the frequency, they would always got this constant number, 3 times 10 to the 8th meters per second. Didn't matter if it was, let's say, X-ray waves, radio waves, you always get the same number. Now, let's check your math skills. I want you to rearrange this equation and find what both the wavelength and frequency are equal to. Okay, so rearrange it, figure out what wavelength is equal to, and what the frequency would be equal to. I want you to fill in these questions, but I want to do maybe the first part together so you can know what I'm looking for. So the question is, explain both 1 and 2 using the equations, the frequency is equal to c over wavelength. So what happens to the frequency if you have a long wavelength? If you have a long wavelength, that means, well, long wavelength, will you have a big number or small number? If it's very long, you'll have a big number, right? Okay, so let's see how that affects our frequency, our V. So if you have a number divided by a very big number, what happens to the frequency? You get a small number. So if you have a small number, that means you're going to have a very low frequency. Let's fill in I want you to do 2 on your own. Let's fill in maybe the first part of question 3. So it says fill in the relationship. If you have a very high energy, what do you think would happen to the frequency? So think of energy as like you're moving really, really fast. If you're moving very, very fast, what would the frequency have to be then? Very high, a high frequency. Okay, so if the frequency is very high, so that means the frequency is just going like crazy, the wavelength. Would the wavelength be short or large? Remember, the frequency is going to be from crest to crest, or sorry, the wavelength is going to be from crest to crest. So here we would see that the wavelength is very small. Therefore, we would have a very low wavelength. Okay, now, in the very last part, you have to fill in the blanks. The blanks that you need to fill in are going to be either directly proportional, so that means if one goes up, the other one goes up, or vice versa. And the other fill in the blank is going to be inversely proportional. Inversely means if one goes up, the other one goes down, or vice versa. They're inversely proportional. So I want you to go ahead and finish the remaining questions on this slide. Question: what is the frequency in hertz of a blue light that has a wavelength of 436 nanometers? Let's do this problem together. So we are looking for frequency. Frequency is that V, that funny looking V, or which we call nu. So we need to figure out, first of all, what nu equals. And from the previous few slides, we would see that the frequency is equal to c, which is the speed of light, divided by the wavelength. Okay, so let's kind of plug in our numbers and see what we have. So the frequency is going to be equal to the speed of light. The speed of light is constant. The speed of light will be 3.00 times 10 to the 8th meters over seconds. And then we have to divide that by the wavelength. Okay, and they give us the wavelength, which is blue light, which is 436 nanometers. Okay, now, can I just go ahead and divide these numbers to get the frequency? I can't, and the reason why is because of these units. Notice that meters here and nanometers here, they're not going to be able to cancel. We need to get these to cancel. And the reason why we need to get them to cancel is so that we can end up in hertz. Remember, hertz is going to be the same thing as 1 over seconds. We have our seconds, right? It's 1 over seconds. We have that, but we need to get the meters and nanometers to cancel off. So what I'm going to do is I'm going to convert, let's say, nanometers to meters. So I'll set up a unit conversion. What unit will go on bottom? Nanometers. What unit will go up on top? Meters. Now I need to figure out the relationship with this. I know that for every 1 meter, there is going to be a ton of nanometers. Nano means a billion. So that's going to be 9 zeros. I don't want to write out 9 zeros. That would be a lot of time. So I'm just going to use this scientific notation and do it 1 times 10 to the 9th. Our nanometers cancel off. Now you could mathematically solve this 2 different ways. You could either do it all in one step, which I like to do because it just saves some time, or you could take the top and then divide it by, and then just the bottom. So you would have to do that calculation, 436 divided by 1 times 10 to the 9th, figure out what that number is, and then divide the top by bottom. Okay, so I just did it in one big step, and when I did it, I got 6.88 times 10 to the 14th. And okay, and now what units will I have? Well, now my meters will cancel off. One's on top, one's on bottom. And I'm going to be left with 1 over seconds, which is the same thing as inverse seconds, right? But they want the answer to be in hertz. So what must I do? Well, because I have 1 over seconds, that's going to be the same thing as hertz. So my final answer will be 6.88 times 10 to the 14th hertz. Now make sure that you can get this number, 6.88 times 10 to the 14th. If you can, then it's going to be fairly difficult to do other problems in this chapter.